Okay, hello. Today we're talking about Codeforces Round 708. So this was a Div 2 round. Unfortunately, it was unrated because of the server issues. Hopefully people weren't too disappointed about that. It always sucks to start with a contest and then solve some problems and then end up unrated afterward. But anyway, I wonder if that will affect the number of viewers today. I assume it'll be less than usual. But either way, we can still talk about the contest, talk about the problems, and yeah, basically, overall, this is definitely this is definitely a weird kind of distribution. Um, Seems like the authors, well, maybe they expected that E1 was pretty easy. I'm not really sure. I mean, this is like a way higher solve count than D. Like they probably could have called ED and vice versa, but it doesn't really matter that much, I guess. Um, Ultimately, I think D was worth just slightly more points than E2. So E1 and E2 were both 1500 and D was 1750. And so in that sense, I guess they got this right, with D being the hardest one. But in terms of other stuff, yeah, I guess B had a decently big drop from A, whereas C1 had more solves. And the funny thing is C1 and C2 are almost the same. So yeah, I guess we'll talk about that in a bit. I'm curious what people thought. Did you guys like the problems? Did you dislike some of them? What were you frustrated about? I'm seeing a couple people liked C. Someone liked B. Someone said B was difficult. B was weird. I see. Yeah. E1 was way too easy. Yeah. Yeah. So for me, I had a pretty funny contest where I started 3 minutes late. So I thought that might cost me, but then I just kind of went through and did all the problems. Geothermal finished all the problems first, but he had 3 wrong submits, and so I actually finished and ended up in first place. But then a while later, I was looking at my A and I realized what I did was just totally wrong. So ended up resubmitting it, and so dropped to second. Yeah, maybe I'll submit my wrong A later and see whether it would have passed the sys test, but I think it's just so wrong that I don't see how it could pass. I'm surprised it actually even passed pretest, but that's really just my bad for messing it up. Anyway, yeah, we can start talking about it. I don't know if they're starting some system testing even. Okay, I guess they're just starting and it's kind of resetting some of these. Anyway, let me see. Let me pull up the problems. Okay, oh yeah, and we had a hydrate, so. All right, let's see. So problem A. Oh, Tankman, you got failed system test. Yeah, well, I guess I mean, I had a wrong submission that passed pretest, so I guess A might have some failed system test. The thing is, I looked at the other submissions in my room and I didn't see anything that was wrong. Nice haircut, thanks. Yeah, my hair was getting a bit long earlier, so. Okay, so problem A. Basically, you have an array. It's not too big, size is up to 100. The elements are between 0 and 100. And you basically want to reorder the array so that the sum of the mix of every prefix is maximized. So I kind of thought this, I mean, this problem, you know, it doesn't end up being too hard, but I thought this was kind of complicated to explain as a div2a. Like, first you need to know what mex is, and that's explained here. It's the smallest non-negative integer that is not in your set. and then you need to think about the sum of the mechs of the prefixes, and it's just like not super intuitive to wrap your head around unless you've had practice doing this type of problem. For me, obviously, I've seen mechs before. I know how it works, and so basically, if you think about it, it becomes clear that the there we go. The I guess I'll make a file. Let's say you have you know, an array like this. Eventually, if you think about it, it just becomes clear that you should set it up to get the array like this: 0, 1, 2, 3, 4, and just go as far as you can. And then once we don't have a 5, then we'll never get a mex bigger than 5. That's one key property of mex, and so you can just throw the extra elements after that. And so if you have another array that's like 1, 1, 1, 0, 0, 0, 0, 2, something like this, you would just do 0, 1, 2, 3, and then you would fill in the extras. So I think there's 4 more zeros, 2 more ones, 2 more twos. And the order of these doesn't actually matter. The only thing that matters is that you do this prefix properly. Checking chat. Okay, yeah, and so yeah, basically you just implement this. There's like a couple different ways you can do this. You can, what I did is I didn't depend on the, oh, this code is just to compute the score, but I didn't depend on the range of values. So I just took the array, sorted it, found the kind of like equal ranges, and then put the first one into the prefix, and then just put all the rest of them into an extra section. So this code is a little bit like more complicated than you would kind of expect from a div2a. There's like a couple different ways to do it. Maybe I'll code up a different way. I can just do that right now. Yeah, I'll code up a different way that is probably a little bit easier. So let's see, I'll call it a map. So I'm going to use a map as a frequency counter, and yeah, basically, so we don't need to sort actually, we don't need a at all. So basically read a and then increase the frequency, and then what we're going to do is we're going to go through the map. Sorry, it should be, and then we're going to take the first, just take one instance of each thing in the map. And the map, one thing to note for C++, map is sorted. So this will give us the keys in sorted order. And then the only thing to do left is to go through the map again. And now we have this. Okay, so yeah, so this should work. I don't know if I can submit this right now because it's going through system tests, so yeah, I don't think so. We can try this later, but yeah, basically this is one quick and easy way to do it. Yeah, another thing is because the numbers are small, you can just make an array of size 100. That would also work. A lot of different options here. You can even do n squared. That's also fine. Just to make sure you do it correctly. My first submit, I did something really weird and ended up being wrong. So that was unfortunate. But anyway, a couple different ways to do it. Checking chat. What did I do wrong? Yeah, I just had this like pretty dumb loop where I just went up and I checked if things were equal, and if they were equal, I like tried to erase it and put it at the end, but then it doesn't even handle properly when there are 3 of the same thing. So let's see, one test case. So here's an example: 0, 0, 0, 1, 2, 3, 4. Is that enough? 7. Yeah, it doesn't even grab like all the zeros. It only did one of them. So yeah, it's just wrong. I'll say maybe like showing up a little late. I was like in a rush, and then I coded this really dumb thing that didn't work. But anyway, yeah, I should just like not mess it up in the future. How did that pass pretest? Yeah, I guess there are no pretests with 3 of the same number. That must be the only thing. But yeah, but ultimately, yeah, it's on me for writing something just super wrong. You know, I don't think that pretest should be just like always 100% inclusive. Okay, so let's see. Is there gonna be anything interesting from watching this? Not really. I guess won't even see my A until much later. Okay, so let's just go into problem B then. The simple one that I just coded. So you can just, it's here, but you can just rewind this video. So I will put a link there, and you can get a replay of the current stream, and you can just pause at any moment you want if you want to look at the code more closely. So yeah, so I'm going to go into problem B. So problem B, you got an array, and the array size n, and you have an integer m. And you want to break up this array into multiple arrays. You can reorder things as much as you want. And for the arrays you end up with, you need every two adjacent numbers in those arrays to add up to a multiple of m. And if it's just an array of a single element, it's always good because there's no adjacent values. So you want to set it up so you divide this into the smallest number of arrays. Okay, so the key thing for this problem is that if two things add up to a multiple of m, then they're negatives of each other in mod m. Yeah, so you need to know a bit of modular arithmetic here. You can read, one of these articles if you're not familiar. But basically, what we're gonna do is we're gonna take every number and just take it mod n, right? Because, for example, here n is 6 and m is 4. Basically, there's no difference between 2 and 6, right? They're both 2 above a multiple of 4. That's the only thing that matters. So you can treat these numbers as the same. And in the same way, you can treat 8 and 4 as the same. They're both 0 mod 4, or multiples of 4. So yeah, so we're just going to take every number mod m. And then basically what ends up happening is for every value mod m, for example, if m is 4, then if we think about 1, we have to put it next to 3. And for 3, we have to put it next to a 1. So they both kind of go together that way. Okay, and so let's see, I guess I'll save that. And so let's take an example where m equals 10, and then we have like a bunch of 3s and 7s in the array. So basically, in any array with a 3 or a 7, there can't be any values other than 3 or 7, right? If you put a 1 in there, it just wouldn't work. If you put like a 2, a 6, whatever, because something would have to be adjacent to a 3 or a 7 that wasn't a 3 or 7, and then it just wouldn't work. And so if we want to make arrays with these two numbers, we also are going to have to alternate them like this. And so that's kind of the general idea of how we set this up. And the question is, how many arrays do we need for example, this specific setup? So if we do it like this, then we still have 3 extra 7s left over. We can notice that we can put 1 at the beginning here. So we end up with 3 arrays. And it turns out that in general, the number of arrays you'll need is just the difference between, the number of, in this case, the number of 3s and the number of 7s. Unless they're the same, if they're exactly the same, you still need one array, right? You can't use 0. So yeah, so that's the general idea. It's just the difference between the counts of those two opposites. There is one special case where the opposites are kind of the same. So for example, 5 is the negative of itself modulo 10. So for example, if we have a bunch of 5s, this is actually one array and we're good, because 5 plus 5 is good. And then actually the same thing is also true for 0. So if we have a bunch of 0s, we can just keep them. So if the number is the negative of itself, the answer is just 1. Otherwise, it's basically, yeah, max of difference of the counts and 1. And then you just need to make sure that there is actually, like this number does actually show up, because if it doesn't, then you're just going to skip it. So my code just looks like this. Frequency array, take it mod m, increment the frequency, and yeah, I just get all the kind of xy pairs. So y is going to be m minus x mod m. That's the kind of opposite of x. And then I have the two cases. If x equals y, so if it's one of these two cases, the answer is just 1. Or specifically, the answer is 1 if frequency x is not 0. So that's why I just add like Boolean of frequency x. Otherwise, I just, again, make sure that the frequency is not 0, and it's just max of difference in 1. Yeah, okay. So another funny thing is I can actually just remove this section because it's covered. It just happens to be covered by this part. But the more important thing is just to think about the logic here, and to make sure you kind of go through it carefully and analyze it, and then you should be good. Yeah, and it's also important, we use the fact that m is small to make this frequency array. But you could even do it if m were big. We would just make a map instead of an array. So similar idea to A. If you missed the explanation, you can basically rewind or replay the current stream at this link. So if you go there, it'll just be the first one, and you can rewatch the section that you wanted to go through again. Let's see, is anything new happening? Okay, so yeah, so geothermal definitely won, and I guess a couple more things to test, so we'll see. Why is the number of rays the difference of the counts between the two negatives? Yeah, so it's basically just this example. M equals 10. We have a bunch of 3s, a bunch of 7s. We should just, yeah, you should just think about this. Basically, your goal is to kind of pair them up with each other. And yeah, I think for this, it just helps to work through a lot of different examples. I just showed one example here. Well, 2 examples. This is also one. But just work through a bunch of different examples on this, and you'll see kind of the pattern. Okay, yeah, so we'll move on to problem C. Yeah, again, like I said, I thought C was funny because there's an easy version and a hard version here. But honestly, the hard version is like, you can just convert it into the easy version. Okay, so let's talk about it. So here's the easy version. In this problem, k equals 3 always. So you're given a positive integer n. You want to find k positive integers a1 through ak such that their sum is n, and their LCM, the least common multiple, is at most n over 2. And yeah, they have to be positive integers, so we're not messing with like any zeros here or anything like that. We can show that it always exists, so it's always possible. Okay, and n is always between 3 and 10 to the 9th. K is always 3. Okay, so for this problem, oh, and I guess I should mention, yeah, so for the hard version, k can be anywhere between 3 and n. Okay, so for this problem, actually one of the first things that I noticed was k bigger than 3 isn't actually any harder than k equals 3. What you do is essentially, for example, let's say you have 9 and 5. Well, we just take a bunch of 1s until we get k down to 3. So we'll just have we'll take 2 1s, right? And then n will be 7 and k will be 3. And so we're just solving this problem for n equals 7. And also we know that it's going to work. So we know that a solution here will just give us a solution here. Yeah, so basically if k is bigger than 3, we just take k minus 3 ones and put those in our array A. And the ones, the key thing there is the ones will not affect the LCM. So we can just reduce the problem from the hard version to the easy version, right? So now let's just solve the easy version. Okay, so cool. We just need to do that. So basically, I was trying some different examples. Let's say n is odd. All right, we started with n equals 19. Let's start with that. What do? We need 3 numbers that add up to 19, and their LCM has to be at most 9. And this one turns out to be really easy. I was just like, okay, what if we use a 1? And it's like, okay, let's just use 199, right? So you can see that in general, if n is odd, you'll just do 1 and this number twice. And then you're good. And that works for any odd number. You can try some other numbers. For example, 15 is 177 and so on. Cool. Okay, so now what do we do for even? Let's say n equals 18, right? Well, 1's not good anymore because then we end up with, we end up with 1 and then 17, and we can't really split 17 very well. 17 is also prime, so it's really not going to split that well. So we're kind of already lost if we pick 1. So we're not going to pick any 1s. Let's try. Oh hi, is this the this is the author, isn't it? Shishin. What happened to my browser? There we go. Yeah, it was unfortunate, but yeah, I mean, it's just my fault for writing really, really dumb code that doesn't work. But I was a little surprised that the pretest didn't have any like triple repeat. It's not necessarily a bad thing because, I mean, I think often people are expecting way too much from the pretests. But probably for div 2a, I would want like stronger pretests. Yeah. Okay, so yeah, so for n equals 18, let's try 2, and then it turns out we end up with 16. We can do 2, 8, 8, right? And that works. And okay, cool. So can we just use 2 for every even number, right? Let's try 20. Well, for 20, we're going to end up with 299. And now we have a problem because the LCM is going to be 18 and not 9. So in particular, 9 is odd, right? So this strategy only works for numbers. If we try to generalize it, it works for numbers that are even, but they're not multiples of 4, right? For 20, it turns out, if you try more things, what you actually want to do is 488. And we'll also notice that 20 is a multiple of 4, but it's not a multiple of 8, right? So there's something interesting going on here with powers of 2. Yeah, and it turns out that the key thing here is what's the biggest power of 2 that's a divisor of n. So, for example, if 2 to the k divides n, but 2 to the k plus 1 does not divide n, I don't know how to write that here. I guess something like this. Then we'll essentially just end up using 2 to the k, n minus 2 to the k, divided by 2, twice. But there is one special case. The special case is if n itself is a power of 2. N itself being a power of 2 is a little weird. For example, n equals 16. Then 2 to the k would be 16, so that strategy above would tell us 16, 0, 0, which is no good. So instead, when n is a power of 2, what we do is n over 4, n over 4, n over 2. And then we're good. So in this case, it's 4, 4, 8. So yeah, so basically it's like 2 cases. One case is the power of 2, and then the other case is not a power of 2. If it's not of a power of 2, then yeah, we find this biggest power of 2 divisor, and we just cut it like that. So again, the example above was 20, then 2 to the k equals 4, so then we just do 4, 8, 8. Another way to think about it is if we write a number in binary, then what we're going to do is we're just going to look at the smallest bit. So right here, this 1. And we're going to take that as one of the numbers. And then the remaining number is 11000000, right? And we'll just take that number and then just divide it by 2 twice. And so these are the 3 numbers we get, essentially. So what if n equals 32? Well, this is just the case we described here. It's just n over 4, n over 4, n over 2. So they don't, the problem does not allow k that big. K can only go up to 10 to the 5th. Otherwise, yeah, I mean, if k is 10 to the 9th, you can't output everything in time. I mean, if n is prime, then n is probably odd. We'll just do this approach, right? Oh, I mean, it's definitely odd because 2 is not even allowed. But yeah, it's just, this problem just kind of comes down to trying lots of examples. You see the pattern for odd numbers, and then you think maybe this 2 strategy works for even numbers, but you realize, no, it only works for even numbers that are not a multiple of 4. For multiples of 4, you might have to do this strategy, and then you realize this actually just keeps going up. It's really about like, how many times can you divide it by 2? So the code ends up looking like this. So here's the code to convert from the hard version to the easy version. That's actually literally all it is. You just make a bunch of 1s. And then otherwise we're going to use this, yeah, we're going to start k equals 3, use this function to solve the easy version, and insert that at the end and output it. And the easy version looks like this. So first of all, n has to be at least 3, of course, otherwise they won't be positive. This is the power of 2 case. So n over 4, n over 4, n over 2, like we said. And then otherwise, I use this little thing here. So this is actually not quite what I submitted, but this is the better way to, like the shorter way to code it. This is a little trick from Fenwick trees where you take basically the lowest bit value of the number. So for example, for this number in binary, it extracts this. And yeah, then I just take x, n minus x over 2, n minus x over 2. And the reason this works in general is because if we're not a power of 2, and this is like the lowest 1 bit in the number, obviously after we subtract this out, right, this value, this will definitely be a multiple of this number because all of these are going to be zeros. And so that's the reason. Yeah, so that's the idea there. Yeah, I think the funny thing was, it seemed like half of the people who got C1 didn't realize that C2, the hard version, is really just, yeah, setting up a bunch of 1s. So I would suggest, I think people might have like solved C1 and then kind of got scared away from C2 because it seems a lot more complicated, right? It's like, oh, k could be anywhere from 3 to n, right? But it's worth trying these little simple things to see if the problem just reduces really nicely. Okay, so I passed everything. That was pretty expected. I had to fix my A though. I do want to submit my wrong A later and see it probably fail. Hopefully fail, otherwise I could have been first without resubmitting. What does problem locked mean? It means that basically, yeah, it means that you lock the problem. You can't submit it again. You can't resubmit it. So whatever you submitted, that's your final submission. But now what you can do is you can go to your room and I did this, and you can go open like other people's submissions to the same problem. So you can go read their code, and then if you think it's wrong, you can try to hack them. And hacking them, if you're successful, you put in a test case that breaks their code, and your test case successfully breaks their code. Then you get some extra points. You get 100 points. So the reason I was trying to do this was because I realized I had to resubmit A, and so I lost a bunch of points there. But if I had gotten 2 extra hacks, that would have been enough for first. And so I just took a look at the other A submissions in my room. Unfortunately, nobody else was quite as dumb as me in terms of failing the problem. They all seemed like they had correct code, so there wasn't anything there. So I just kind of left after that. Oh yeah, sometimes the actually it looks like that was not the case here, but sometimes the authors will say that you cannot hack the easy version unless you solve both of the versions. Yeah, I don't know if Shishin is still here, but is that something that you thought about? Because, for example, you have 2 problems with subtasks, C1 and C2. So was that already the case? You have to lock both problems to C? Because it didn't mention that here. And I actually submitted my full C version for C1. So it's possible that, was it possible that someone could solve C1, not know how to do C2, lock C1, go read other C1s, and then read code that works for C2? No, not possible. Okay, so I guess Codeforces set up subtasks now so that you just can't do that. But it was usually mentioned in the problem statements in the past. So that's what I was wondering. Interesting. Okay. Yeah, Shishin, if you're still here, I'm curious if you had any comments. But yeah, let's see. We talked about C, and so okay, so D is actually the hardest problem, so I will save D for the end. So for problem E, let's see. I guess we can talk about the easy version and the hard version separately. Yeah, oh, so pretest versus sys test. So I believe it's not actually because the point is to speed up the testing. I think it's just intentional to, not have the full system tests as the in-contest tests. And there are different ranges of how contests or where contests fall on this. For example, AtCoder gives you the full ACE or whatever verdict on the full set of tests. Whereas, for example, on Topcoder, you don't have, there are no pretests at all. There are just samples, and you can submit even if you don't pass the samples. And so, Topcoder ends up being, the challenge phase ends up being very important. And personally, I really enjoy the challenge phase, so I really enjoy that aspect of Topcoder. For Codeforces, there is hacking, but it's kind of becoming more and more the case that there just are no hacks to be found. For example, this contest, I think there was 1 hack in the entire contest, which is pretty boring, I would say, and unfortunate. But yeah, personally, I like more of the Topcoder setup where there is this interesting strategic element of challenging and hacking and so on. And so it's not just about how quickly you can solve the problems, but also about, can you understand other people's approaches to the problems? Can you kind of dissect their code and figure out what's going on? So I think it adds another fun layer to the contest. Okay, so we can talk about problem E. Yeah, so definitely product must be a square. This idea has shown up before. So let's talk about this quickly. So first of all, we have a bunch of positive integers. We want to divide it into the smallest number of segments so that each segment has no two numbers whose product is a perfect square. There's also a setup where you can do k operations where you change a number in the array to any other number, any other positive integer. In E1, k equals 0, so you can't do this. In E2, k is up to 20, so you can do this up to 20 times. And yeah, the question is, what is the minimum number of segments you can end up with? N is up to 2 times 10 to the 5th. AI are up to 10 to the 7th. So yeah, first of all, the AI should be limited. This way we have enough time to actually factor them. So we start by doing a prime sieve and then setting up this code to prime factorize the values. And yeah, key observation here. So basically, if we think about two numbers, A and B, and we think about when is A times B a perfect square, well, if we think about the prime factorizations, and so on, and B is something similar, then if we look at the prime factorization of A times B, it's going to look like a similar form. Basically, what it means is that for every prime, the exponent of A plus the exponent of B for that prime is even. So if we think about the prime's exponents as being either 0 or 1, like taking them mod 2, then we can kind of convert each number into a sort of canonical form of the number. So for example, if we have the number 18, right, then x equals 2 times 3 squared, then we can just convert this to x equals 2, because the 3 squared just like doesn't really affect anything. And similarly, if x equals 8 and x equals 2 cubed, then we can also convert this to x equals 2, because this 3 just functions the same as 1 in terms of perfect squares. So it's just really, is it 0 or 1 mod 2? So we essentially convert every number into the product of their prime factors that have odd exponents. And then once we get to that form, two numbers multiply to a perfect square if and only if they're the same. So this is a really nice way to simplify the thinking around the problem. And so, yeah, kind of the first thing I said was this function. So we start with calling the sieve on 10 to the 7th. And then when we get a number A, to make it its canonical form, we prime factorize it. And for all of the, like we said, for all of the odd exponents, we multiply by that prime and return that product. So yeah, that's the first thing we do. We just read the input, turn everything into its canonical form. Yeah, and then for E1 is really easy because we're just saying, oh, we have an array. What's the minimum number of subarrays we can, or yeah, segments we can divide it into so that no segment has a repeat number. And that's just a pure greedy. So we just go through from left to right. If this number is already in our segment, we just cut off the segment right here and start a new segment. And that gives us the answer. So that's E1. So yeah, so if you haven't done prime sieve before, that's an important thing to learn for this problem. So I believe it's the sieve of Eratosthenes. And there's an algorithm for this. It runs in n log n time. Here n is 10 to the 7th because that's the limit on the numbers. And another key thing to track is this smallest factor value. So this gives you the smallest prime factor of a number. And using this is how we end up factoring each number. So we just kind of repeatedly grab this value. Yeah, so that's basically the idea for E1. Now for E2, what's going to happen is we can change up to 20 of the values, right? So the first thing we should realize is when we change a value, we should just change it to something just completely different, just like some huge random prime number that's much bigger than anything here, and that will never conflict with anything, right? And so it's almost like we can treat it as, instead of changing a number to a different number, we can just treat it as deleting the number, because changing it to some huge random prime will do that for us. Okay, so now we kind of have converted this to a new problem where essentially we start with an array. We need to divide it into segments where no segment contains a repeat number, but we can change k of the numbers. And so, yeah, this kind of screams DP, right? Because it's kind of like, given this prefix of the array, given that we've changed this many numbers, what's the minimum number of segments we can have? And so that's kind of the general thinking around that. That turns out to be the state that we want. This is just some code that I set up to compress the values of a, so they fall between 0 and n. Yeah, and then a key thing here is to figure out, okay, so if I start from this position in the array, and I can have up to this many repeats, how far can I go? That's important for our transition function. So I'm just going to give a high-level overview for this problem, since it's one of the hard problems. But basically, let's say we have, okay, I don't want to make up random numbers, I'll just generate random numbers. Oops. Let's see, 10 numbers between 1 and 5. Yeah, okay. So here's some random numbers. So if we think about, starting here, well, let's say starting here. If we are allowing up to, let's say 3 repeats, how far can we go? And that would let us go up to here, because this 2 is a repeat, this 4 is a repeat, and this 4 is a repeat. And this 4 will make a 4th repeat, which is not good. So that's basically what we need to know. Basically, for each starting position and for each number of repeats up to 20, how far would we be able to go before we have too many repeats? And so that's what I'm computing here. It's transitions. So transitions I, k is exactly what we're saying. Starting from I, allowing k repeats, how far can we go? And that's pretty simple. You just go from right to left in the array. You track the closest position of each value. And then I just have this kind of recent array. In context, I used a Fenwick tree, which is totally unnecessary. You can just use a vector. And yeah, basically, we're going to make an array of those closest values, set up these transitions, and for example, when this is our starting point, we're going to basically mark all of the values that are repeats of something before. So if we want to know how far can we go with 0 repeats, we have to stop before this one. How far can we go with 1 repeat? We have to stop before here, right? So we can go this far. How far can we go with up to 2 repeats? We have to stop before here, so we can go this far, and so on. And so that's basically the transition table right there. Give me 1 second, I'll be right back. Okay, so that's our transitions table, and then we're going to create our actual DP values. Yeah, and DP, it's a 2D table. So basically, what do we have here? Transitions ik equals how far, starting from I, if we allow k repeat values, how far can we go? And then dpik is going to be for the prefix from 0 to I minus 1, if we allow, or if we use k changes, what's the min number of segments? I did have to get a refill. Yeah, and so these are our two values. So for the dp table, what we're going to do is, if we start from I, then we're going to go through, each value of repeats in our current segment, and we're going to go through each kind of starting value repeats in our prefix, and we have this dp transition. So dp and a plus b, so b is how many we had before the segment, a is how many we're going to do in the segment in terms of repeats. And again, a plus b has to be at most k. Basically from I, b, if we use a repeats, we can get to end. This is our transition table with one extra segment. And so that's the dp transition here. And then the answer is just the min value of any dp value with the whole array. So this ends up being, this is n times k squared. Here n is 2 times 10 to the 5th, k is 20. So that's not too big. It's about 80 million. But I guess one key thing is, because of this a plus b is at most k, we get it divided by 2, so it's like 40 million. And so that's definitely fast enough. I think my submission was quite a bit under the time limit. Yeah, 400 milliseconds, so definitely a good amount under. Once this is done, I can submit a couple of things. We'll see if this is the wrong answer. I'm pretty sure it will be. Is the min element needed, or can I just print? Yeah, I mean, I can probably just print dpnk. I just didn't want to think about it too much. I guess the thing that I was like trying to be careful around was, let's say k is like a lot bigger than n. Do we have a problem in that case? I need to like actually, let's just print the whole dpn array. Okay, so 1, 220, and the a are like 1 and 2, like whatever. Yeah, so maybe it's fine. I could probably just print dpnk, but it doesn't really cost anything to just do min element, so I just went ahead with that. Do you ever get memory limit exceeded? Yeah, definitely have gotten memory limit exceeded before. The main times that happens, I guess there was some E2 fail here in my room. Wrong answer on test 61. Huh. Wow. So that's, but yeah, I was right that there were no A hacks for me. Maybe we can peek at just how many system tests are failed in general. So there's only one hack, which is what I saw. We can look at rejected based on judging time. Yeah, so some amount of A's. Okay, so I kind of did expect there would be some A's given my submission. Definitely a decent amount of wrong or TLE on E1, E2. A little bit of C1. There's some TLEs on C1. So this is rejected sorted by judging time, and so this will be the failed system test basically. Yeah, a lot of A wrong on test 4. So yeah, I think this is probably because of a similar thing like I set up, but no one else in my div 1 room made this mistake. Can I give an example where greedy replace would fail for E2? Ah, okay, that's a good question. So for E2, so what is the greedy replace? It's just like go left to right and replace the first thing each time. We did skip D. Yeah, D is the hardest problem, so I saved it for the end. Yeah, let's think about this greedy for E2. So let's see, does this work? Yeah, I think this is a good example. So let's say we have this array and k equals 1. So we can change one thing. So if we have this, you know, and we go left to right in greedy, we'll be like, okay, 1 is good, 2 is good, and then we're like, oh, another 2. So we'll change it to 3. And now we'll end up with 3 segments, right? Because we have too many 1s. So what we should have realized is that, oh, actually it's not better to change this 2, it's better to change this 1. So instead we should have done 1, 2, 2, 3, 1. And now we can just cut it once here. Yeah, so that's an example where greedy fails. That's why we need to do this DP. Oh, Codeforces is down again. Okay, well, it's back. Yeah, I'm pretty sure I would have been this wrong answer in test 4. So I guess it was good that I resubmitted. Okay, so one problem left. We have problem D. Let's talk about that. So problem D is aptly called genius because it is the hardest problem here, I guess. And it has a unusually small memory limit. I'm not really sure why they want to do that. I guess I set it up to use O of n memory rather than n squared. But anyway, I thought this problem was pretty weird. The like the statement, I don't know. It was kind of hard to understand the statement because it was very strange. But eventually, the solution ends up being reasonably nice. But okay, so there are n problems. They're numbered from 1 to n. The ith problem has complexity ci equals 2 to the I. Oh, is it too small? I can make it a little bigger. All right. The ith problem has the complexity ci equals 2 to the I. There's a tag I and a score si. After problem I, you're allowed to solve problem j if and only if your IQ is less than absolute value of ci minus cj and tag I is not equal to tag j. After that, your IQ changes and becomes IQ equals absolute value ci minus cj, and you gain this many points. Any problem can be the first. You can solve problems in any order as many times as you want. Initially, IQ equals 0, and find the maximum number of points you can earn. N is up to 5,000. Tags are between 1 and n, and SI is between 1 and 10 to the 9th. Okay, so for the first example, you should solve problem 1, 2, 3, 1, and 4. And then you get 35 points. And so on. Yeah, so again, this problem is pretty weird. This problem is already confusing from the statement. But the key thing to notice here, the first thing that I notice is, oh, okay, so IQ has to be less than this to start with, and then it becomes this. So that's why we can only make, because the question is like, if we can repeat a problem, why can't we just go forever and get infinite score? The reason is because IQ is always increasing. So IQ will go up to this. Excuse me. And yeah, IQ can't increase forever, so that's where we kind of stop. And because of this 2 to the I thing, there ends up being this like nice ordering on the pairs of problems we can do. So okay, thanks for stopping by, Shishin. For those who didn't realize, Shishin's the author of the round. So they stopped by to say hi. Okay, so let's take like n equals 5. Then there's a bunch of pairs. 1, 2, 2, 3, or 1, 3, 2, 3, 1, 4, 2, 4, 3, 4, 2, 5, 3, 5, 4, 5. Okay. And if we sort them by 2 to the j minus 2 to the I, we actually end up in this order. So maybe if I split out like this, it might be more clear. This is the order sorted by 2 to the j minus 2 to the I. The reason is when you sort in this order, the most important thing is j, right? Because, for example, 2 to the 5 minus 2 to the 4 is bigger than 2 to the 4 minus 2 to the 1. And so yeah, the most important thing is j, and then the second most important thing, the tiebreaker, is to make I smaller, which will make this value bigger. And so this, basically this weird thing here ends up sorting it like this. Okay, so now what we can see is if we take a, kind of a path through here, what we need to do is basically we're picking pairs out of here where for everything we pick, the second number of one row is the first number of the next row that we pick. Or not exactly the second number, but like the number we end up with is the number after 1 is the number we start with for the next one. So we can do 1, 2, 2, 3, 3, 4, and then we can go to 4, 1, right? And so our path is 1, 2, 3, 4, 1. And then we can do 1, 5. And then that's it, because we're out at that point. There's nothing after this. So this would be a potential path. This would be 1, 2, 3, 4, 1, 5. So yeah, it's kind of like a graph. And we're kind of finding like the best path through this graph. It's a bit weird, yeah. And we have to go through in the order of these pairs. Yeah, and we have to check the tags. So some of these kind of transitions may not be allowed due to tags. But this is one potential thing we can go through here. Yeah, so if you think about this, one thing that you end up realizing is if you think about a section here, for example, this is the 5 section, right? We can only pick at most 2 things in a section because we can come in somewhere. Let's say we come in from 3, then we go 3, 5, and then we can go out from 5. We can go out from 5 to like 5, 1, right? Or we can come in at 3, 5, go out at 5, 2. But once that's happened, we're done. We can't get back into this 5 section. What are I and j? Yeah, it's just because of this weird thing in the problem of like ci equals 2 to the I and then absolute value of ci minus cj. And this is just in practice, if you take all the pairs with n equals 5 and you sort them by 2 to the j minus 2 to the I, you just get this setup, this order. Am I doing JOI this weekend? I don't know what JOI is. Is that like Japanese OI? No, I don't do the use of code contests. How does that sort work? Yeah, I mean the key thing you can analyze it, but basically 2 to the 5 minus 2 to the 4 is bigger than 2 to the 4 minus 2 to the 1. That's one perfectly good example to show why J is the most important thing for sorting it. But anyway, moving on. Yeah, so the key thing is we can only get 2 things in a section. So even in like a bigger section, right? 5, 6, 4, 6, 3, 6, 2, 6, 1, 6. We can only get 2 of these. If we come in from 5, we go 5, 6, and then we leave 6, we go 6, 3. That's it. We can't do any of these other ones. So that kind of leads us to do a DP transition per section, where it's like, okay, given that we're currently sitting at some problem, what is the maximum value we could have, the score we could have, and get to here? And we can kind of only do, basically we can only do 2 things per section. So yeah, so we kind of just iterate through each of these pairs in order. And we can try both directions of that pair. So for this pair, we can try going from 5 to 6, and we can try going from 6 to 5. One key thing is to make sure we don't do both at the same time, because that's not allowed. We can't go 5, 6, 5. Yeah, so like I said, the problem is it's kind of weird. It's a little bit hard to understand, but once you do and you kind of figure it out, the solution ends up pretty simple. You have a DP like this. So you just read all the input first. DP tells us, given that we're on this problem, this is the last problem we did, what is the biggest number of points we could have? And then I'm iterating by big. Big is just the kind of section I was talking about. So big for this section would be 6. And then I go for the other number from big minus 1 down to 0. First, you make sure their tags are not the same. and then you just do some transitions. So one thing we can do is go from x to big. That's dpx plus the absolute difference of these scores. We can also go from big to x. That's the other way around. But we can't do both, so that's why we pre-compute these two values and then assign them. Yeah, I think the memory constraint is just to stop an n-squared memory solution. But I don't even know an n-squared memory solution here. I guess you could just have a 2D array of like dp of big and x or something like that. But it's pretty easy to convert like this. So even if you started, like if you thought of an n-squared memory solution, I would just code it. If you get it correct, then it should be fairly easy to juice it. Yeah, and then final answer is just the max value of the dp array. And then we're good. So pretty short code for this problem. This was the hardest problem of this div too. I did feel like kind of understanding it and wrapping your head around the problem was the hardest part. And so that was kind of the key thing here. Let me double check the time. Okay, I need to go in just a couple minutes, but yeah, that covers all of the problems. If anyone has any particular questions, let me know. And in the meantime, I guess we can check out, I think this should be done. Is the site still down? Okay, I guess we won't be checking the standings. I still want to see, I still want to submit a couple things to see, but looks like I can't. Okay. Can I submit? So yeah, I read C1 and C2 both, and I realized that I can just solve C1 and then C2 is pretty easy. Oh, here we go. It's still not done testing, so I won't be able to submit. Yeah, I would definitely be first if I didn't make a mistake in A. No, I'm not doing LeetCode weeklies at the moment. Okay, let's see. We can see which ones are running. I bet there are just a couple that are kind of getting stuck. Is the accurate? Yeah, the accurate DP contest is good for just learning and practicing DP for sure. Oh, for setting problems, yeah, I think it's definitely easier to set problems once you've gone up to a certain level yourself. That way you kind of know the different techniques you can apply, and so you're kind of just more likely to be able to find a solution to a problem you come up with. Okay, yeah, unfortunately, I think the CF is super laggy right now. It's not really going to work. And yeah, we're right at the hour, so I'm going to start to close off the stream. Oh yeah, educational tomorrow. Yeah, I'll probably enter, but I have something shortly afterwards, so I don't have time to stream tomorrow. So wanted to get in a stream today. Yeah, definitely recommend checking out the DP contest, Crow, and Mustafa Keller. Yeah. Cool. Anyway, thanks everyone for coming to check out this stream. Hope to see you all next time. And yeah, if you haven't followed the channel and you can get notifications, you'll see when I go live in the future. Yeah, and then also if you run, I guess I'll just type this in. There's also a Discord server. You can check out the, there we go. Yeah, you can check out the server. You can just chat with the community in the meantime. Oh yeah, and if you need a replay, it's right here. All right, cool. A lot of things in the last 1 minute, but anyway, see you all next time.